There's a hidden ocean of light washing over the universe right now, an invisible sea of energy so powerful it could vaporize planets in an instant, yet we can't see it with our eyes. We can't feel it on our skin. It's the cosmic gamma-ray background, a ghostly glow of high-energy radiation that permeates every corner of space, and despite decades of study, it remains one of the most baffling puzzles in modern astrophysics. Where does it come from? What cosmic engines are capable of producing such relentless, universe-spanning energy? The answers might rewrite everything we thought we knew about the fabric of reality itself. Picture this: every second, trillions of gamma rays, the most energetic form of light, streak through the darkness of space. Some are born in the violent deaths of massive stars, others in the chaotic hearts of distant galaxies. But when scientists try to tally up all the known sources, something doesn't add up. There's too much gamma radiation, far more than our current understanding of the cosmos can explain. It's as if we're hearing whispers in the dark from sources we can't even begin to identify. These aren't just random blips, they're clues to something monumental lurking just beyond the edge of our comprehension. That's where the real mystery begins. Hidden within this gamma-ray fog are 25 cosmic enigmas, each one a tantalizing thread in a much larger tapestry. Some point to the existence of dark matter particles annihilating in deep space. Others hint at colossal structures or phenomena we've yet to imagine. And then there are the anomalies, the signals that defy all expectations, the ones that make scientists pause and wonder if we're missing a fundamental piece of the puzzle. Today, we're diving into these mysteries, unraveling the secrets of the gamma-ray background, and exploring what they reveal about the universe's best-kept secrets. Buckle up, because this journey will take us to the very edge of known physics and beyond. The first great riddle of the cosmic gamma-ray background is its sheer uniformity, a faint, all-pervasive glow stretching across the emptiness of space like an echo from some ancient cosmic event. Unlike the brilliant bursts of gamma rays that flare and vanish, this diffuse light lingers, unchanging and omnipresent. It's not tied to any single galaxy or cluster. It doesn't flicker or pulse. It simply is an unwavering whisper of the universe's most violent energies. So where does it come from? One leading theory points to dark matter, those invisible particles that make up most of the universe's mass. If dark matter particles collide and annihilate, they could produce gamma rays as a byproduct. Picture two ghostly particles smashing together in the void, unleashing a spark of light we can detect across billions of light years. It's an elegant idea, but there's a problem. We've never directly observed dark matter, let alone caught it in the act of annihilation. The signal we're seeing is too faint, too spread out, leaving scientists debating whether we're glimpsing dark matter's fingerprints or something else entirely. Then there's the astrophysical explanation. Imagine countless distant sources: supernova, neutron stars, black holes, each contributing a trickle of gamma rays to the cosmic sea. Individually, they're too faint to spot, but together they could create the background glow we detect. But here's the catch: even when we add up all the known gamma-ray producers, there's still a gap, an excess of radiation with no obvious origin. It's like trying to account for every drop of water in the ocean and realizing there's an entire hidden reservoir we can't see. And that's what makes this mystery so compelling. Every answer leads to new questions. If it's not dark matter and it's not ordinary astrophysical sources, then what is flooding the universe with this enigmatic light? Could there be exotic objects, cosmic engines operating beyond the laws of physics as we know them? Or are we witnessing the aftermath of some colossal, forgotten event, an explosion or collision so vast its echoes still ripple through space? The diffuse gamma-ray background isn't just a scientific curiosity. It's a cosmic crime scene, and every photon is a clue. Solving this mystery could crack open our understanding of dark matter, rewrite the story of how the universe evolves, or even reveal entirely new physics lurking in the shadows. Until then, the universe keeps its secrets hidden in plain sight, written in light we can barely perceive. But the gamma-ray background isn't the only cosmic mystery written in high-energy light. Rising from the heart of our own galaxy like twin titans, the Fermi Bubbles stretch 25,000 light-years above and below the Milky Way's disk, vast structures glowing with gamma rays, yet invisible to human eyes. Discovered just over a decade ago by the Fermi Gamma Ray Space Telescope, these colossal formations defy easy explanation. They're not remnants of a supernova. They're not jets from a feeding black hole, at least not in any way we've seen before. They're something else entirely, a pair of cosmic chimneys pumping out gamma rays with no clear source. So what are these bubbles? One leading theory points to Sagittarius, a star, the supermassive black hole at the Milky Way's core. Every few million years, it might awaken from its slumber in a violent feeding frenzy, devouring nearby gas and stars. Such a feast would unleash unimaginable energy, launching jets of particles and radiation into intergalactic space. Over time, these outbursts could inflate the Fermi bubbles like cosmic balloons, leaving behind a faint, lingering glow. If that's true, we might be seeing the aftermath of a galactic-scale eruption, one that could have bathed our entire galaxy in radiation millions of years before Earth even formed. But there's another possibility. Imagine not a single cataclysmic event, but a chain reaction of star formation, bursts of stellar births and deaths so intense, their combined energy punches through the galaxy's disk. Some astronomers argue that the bubbles could be the fossils of an ancient starburst period, when countless massive stars lived fast, died young, and left behind a tsunami of gamma rays. The trouble is, no known star-forming event in the Milky Way's history quite matches the scale needed to create these structures. Did we miss something? Or does the galaxy have a hidden chapter we've yet to uncover? And then there are the anomalies. The Fermi bubbles don't just emit gamma rays, they do so with a peculiar energy signature, one that doesn't neatly fit either the black hole or starburst scenarios. Some researchers speculate about more exotic explanations: dark matter interactions, cosmic rays trapped in magnetic fields, or even relics from a time when the Milky Way collided with another galaxy. Every new observation seems to deepen the mystery rather than solve it. One thing's certain: these bubbles are a cosmic wake-up call. They remind us that even our own galaxy holds secrets we're only beginning to grasp. Whether born from a black hole's tantrum or a forgotten era of stellar chaos, their existence challenges our understanding of how galaxies evolve. And perhaps most thrilling of all, they hint at forces and events far beyond what we've witnessed in our brief time studying the cosmos. The Fermi bubbles aren't just ghostly relics of the past. They're a roadmap pointing us toward the next great discoveries in astrophysics. Some of the most violent flashes in the universe come from objects no larger than a city, neutron stars, the dense corpses of dead suns. These cosmic powerhouses occasionally unleash bursts of gamma rays so intense they temporarily outshine entire galaxies. But here's what keeps scientists up at night: some of these eruptions don't follow the rules. They erupt without warning, flicker in bizarre patterns, or pack energies that shouldn't be possible under our current understanding of physics. Take the case of the Magnetar SGR 1935 plus 2154, a highly magnetic neutron star that shocked astronomers when it fired off a gamma-ray flare bright enough to briefly ionize Earth's upper atmosphere from 50,000 light-years away. For a split second, this tiny object produced more energy than our Sun emits in 150,000 years. But the real puzzle: current models can't fully explain how magnetars store and release such catastrophic energy. It's like a rubber band snapping with the force of a nuclear bomb, except no one knows where the rubber band came from. Then there are pulsars spinning neutron stars that normally tick with the precision of cosmic clocks. Yet occasionally they too break character. In 2020, the Vela pulsar, usually a model of predictability, suddenly tripled its rotation speed before settling back down, all while belching out gamma rays. Imagine a skater pulling their arms in to spin faster, but this skater weighs more than our sun and somehow accelerated without any obvious force acting on it. Even stranger, some of these bursts arrive with a split-second double pulse, as if the star hiccuped twice in rapid succession, a phenomenon no existing theory adequately explains. What makes these outbursts truly baffling is that they defy the two leading explanations for neutron star activity. The first theory involves starquakes, cracks in the star's ultra-dense crust releasing pent-up magnetic energy. But some observed gamma-ray flashes are 10 times more energetic than what starquakes should produce. The second theory points to magnetic field lines snapping and reconnecting, a process we see on the Sun. Yet the most extreme magnetar flares emit gamma rays at energies that magnetic reconnection simply can't generate. It's as if we're watching a fireworks show where some rockets explode with colors not found in nature. The implications ripple far beyond these exotic stellar remnants. If neutron stars can produce gamma rays through unknown mechanisms, it means there are fundamental gaps in our grasp of matter under extreme conditions, pressures so high that atomic nuclei crumble into quark soup, and magnetic fields strong enough to distort the quantum vacuum itself. Every inexplicable flash is a breadcrumb leading toward new physics, hinting at forces or phenomena we haven't yet imagined. Until we crack this code, the universe's most energetic light shows will remain both dazzling and deeply mysterious. Somewhere in the vast emptiness between galaxies, an invisible battle rages. Cosmic rays, subatomic particles accelerated to near light speed, race through space, while gamma rays, their high-energy counterparts, streak alongside them. Scientists long assumed these two phenomena were cosmic partners, with gamma rays acting as fingerprints left behind by cosmic ray collisions. But the universe, as always, has proven far more complicated. Take the case of our own galactic backyard. When cosmic rays slam into interstellar gas, they should produce gamma rays with predictable energy signatures like skid marks at the scene of a particle collision. And sometimes they do. Yet when astronomers compare maps of cosmic ray hotspots to gamma ray emissions, the match isn't perfect. Whole regions glow with gamma rays where there's no corresponding spike in cosmic rays, while other areas rich in cosmic rays remain oddly dim in gamma light. It's as if the universe is playing a shell game, hiding the connection between these two fundamental forms of energy. One clue lies in the interstellar medium, the thin soup of gas and dust filling the space between stars. Imagine cosmic rays as marathon runners and the interstellar medium as a hazy obstacle course. Some particles might crash into gas clouds, creating gamma ray bursts in the process. Others could get deflected by magnetic fields, their paths twisting in ways that scramble the expected gamma ray signal. And then there's the dark matter wild card. If some gamma rays come from invisible particle annihilations rather than cosmic rays, that would explain why the maps don't always align. But the plot thickens beyond our galaxy. In the distant universe, ultra-high-energy cosmic rays particles with energies millions of times greater than anything our most powerful colliders can produce travel for billions of years before reaching us. Along the way, they should interact with the cosmic microwave background, creating a predictable cascade of gamma rays. Yet when astronomers look, they find fewer gamma rays than expected, as if these extreme particles are slipping through the cosmos undetected. Some theorists propose they're transforming into exotic particles along the way, while others suggest we're missing entire chapters in the story of how energy propagates through space. Every mismatch is a crack in our understanding, revealing how much we still don't know about the invisible forces shaping the universe. Solving this riddle could rewrite the rules of particle physics, expose hidden properties of the interstellar medium, or even uncover entirely new cosmic phenomena. For now, the missing link between gamma rays and cosmic rays remains one of astrophysics' most tantalizing loose ends, a reminder that even the most fundamental connections in the universe can hide astonishing secrets. The Andromeda galaxy, our closest cosmic neighbor, holds a secret cloaked in high-energy light. Unlike the Milky Way's concentrated gamma-ray emissions from its bustling core and Fermi bubbles, Andromeda wears a faint but unmistakable gamma-ray halo, a diffuse, spherical glow stretching far beyond its visible disk. This discovery, made by the Fermi Gamma-Ray Space Telescope, caught scientists completely off guard. Why would a galaxy strikingly similar to ours radiate gamma rays in such an unexpected way? The first clue lies in the halo's sheer size. Imagine wrapping Andromeda, a spiral galaxy 2.5 million light-years away, in an invisible sphere of energy so vast it could swallow multiple Milky Ways whole. Unlike the Fermi bubbles, which rise vertically from our galaxy's center, Andromeda's gamma-ray emission forms a near-perfect cocoon. This symmetry suggests something fundamentally different is at play. One leading hypothesis points to dark matter, the universe's most elusive substance. If dark matter particles cluster more densely around Andromeda than our own galaxy, their collisions could produce this distinctive halo. Picture trillions of invisible particles annihilating in slow motion, each collision sparking a gamma-ray photon that contributes to the glow. Yet there's a problem with this elegant theory. The Milky Way should theoretically harbor just as much dark matter as Andromeda, yet our galaxy lacks this pronounced halo. Some scientists argue that Andromeda's turbulent history, its past collisions with smaller galaxies, might have stirred up its dark matter, increasing annihilation rates. Others propose that we're simply seeing the aftermath of cosmic ray interactions on an unprecedented scale. In this scenario, high-energy particles, accelerated by supernova or black holes, escape Andromeda's disk and collide with intergalactic gas, creating gamma rays as they go. But the plot thickens when you examine the energy spectrum of Andromeda's halo. The gamma rays aren't just uniformly distributed, they peak at specific energies that don't perfectly match either dark matter models or known astrophysical processes. It's as if the galaxy is broadcasting a signal we don't yet know how to decode. Could there be an entirely new class of cosmic accelerators at work, objects or phenomena we've never observed in our own galactic backyard? The implications stretch far beyond Andromeda. If the halo stems from dark matter, it could finally give us a way to map the invisible scaffolding of the cosmos. If it's something else, perhaps a previously unknown interplay between cosmic rays and intergalactic space, it might rewrite our understanding of how galaxies interact with their surroundings. One thing is certain, this ghostly gamma-ray shroud is more than a curiosity. It's a cosmic fingerprint left by forces we're only beginning to trace. Some of the universe's smallest galaxies hold some of its biggest surprises. Dwarf galaxies, faint, sparse collections of stars orbiting larger galaxies like our Milky Way, should be cosmic backwaters when it comes to gamma rays. They lack the supermassive black holes, dense star clusters, and frequent supernova that make larger galaxies gamma-ray powerhouses. Yet a handful of these unassuming cosmic minnows shine with gamma-ray emissions that defy all expectations. Their faint glows, barely detectable against the cosmic background, hint at something extraordinary lurking in their shadows, the leading suspect, dark matter. Unlike bright, star-filled galaxies where gamma rays can be explained by ordinary astrophysics, dwarf galaxies are so dim and diffuse that their gamma-ray output shouldn't even register. Unless, of course, something invisible is at work. Picture a dwarf galaxy as a fishing net with holes too wide to catch fish unless the fish are as big as whales. Here, the whales could be dark matter particles packed so densely in these galaxies' cores that they frequently collide and annihilate, sparking gamma rays in the process. It's an elegant solution, one that would finally give us a way to indirectly see dark matter in action. But catching these faint signals is like listening for a whisper in a hurricane. Dwarf galaxies are already challenging to observe due to their low light, and their gamma-ray emissions are even fainter, buried under noise from cosmic rays and distant astrophysical sources. Scientists have to comb through years of data from telescopes like Fermi, teasing out statistical hints rather than clear detections. Even then, the results are maddeningly inconsistent. Some dwarfs, like Draco and Sculptor, show tantalizing excesses of gamma rays, just enough to raise eyebrows but not enough to declare victory. Others, like Fornax, remain stubbornly quiet, despite supposedly harboring similar amounts of dark matter. This inconsistency has led to fierce debates. Could the gamma rays originate from something more mundane, like hidden pulsars or faint stellar remnants too dim to spot directly? Some researchers argue that even a handful of undiscovered neutron stars or microquasars could explain the signal, no dark matter required. Others counter that the distribution of gamma rays, smooth and spread out rather than clustered, points to a more exotic source. It's the cosmic equivalent of finding footprints in the snow. Are they from a known animal or something entirely new? The stakes couldn't be higher. If dark matter truly is behind these emissions, dwarf galaxies could become our best laboratories for studying its properties. Their simple structure, little gas, few stars, and minimal astrophysical chaos makes them ideal for isolating dark matter's signal from the noise. But if the answer lies elsewhere, it forces us to reconsider what we thought we knew about these seemingly quiet corners of the universe. Every flicker of gamma light from a dwarf galaxy is a clue, a piece of a puzzle that might finally reveal the invisible hand shaping the cosmos. Until then, these unassuming galaxies remain both a beacon of hope and a source of frustration, tiny, enigmatic, and utterly indispensable. Some corners of the cosmos appear silent and empty, vast deserts of darkness where telescopes find nothing but the occasional distant galaxy. Yet when scientists train gamma-ray detectors on these voids, they pick up flashes of high-energy light with no obvious source. It's like hearing applause in an abandoned theater, the echoes of some unseen performance. These ghostly signals, emerging from regions devoid of stars, gas, or any known matter, challenge our most basic assumptions about where gamma rays come from. One striking example lies in the so-called empty regions surveyed by the Fermi Gamma-Ray Space Telescope. These areas, carefully chosen for their lack of visible galaxies or galaxy clusters, should, in theory, be gamma-ray quiet. Instead, they flicker with faint but undeniable emissions, the immediate suspicion, instrumental noise or scattered light from brighter sources nearby. But painstaking analysis rules out these explanations. The signals are too consistent, too localized. Something real is happening in the void. The most tantalizing possibility involves dark matter halos, invisible clumps of the universe's missing mass drifting through intergalactic space. If dark matter particles collide and annihilate even in these sparse regions, they could produce the observed gamma rays. Picture an unseen iceberg floating in a cosmic ocean, its submerged bulk invisible except for the faint ripples it creates. The challenge is that current models predict dark matter should be smoother in these voids, not clumpy enough to generate detectable signals, unless, of course, our models are wrong. Then there's the astrophysical wildcard, orphaned cosmic accelerators. Imagine a supermassive black hole, ejected from its host galaxy during a violent merger, now wandering the void like a lone gunslinger. Or a neutron star kicked out of its birthplace by a supernova's asymmetric explosion, still pumping out gamma rays as it drifts through the emptiness. These rogue objects would be nearly impossible to spot with optical telescopes, but could easily explain the mysterious signals. The catch: we've never definitively found such an object in the act of producing gamma rays, only circumstantial evidence that they might exist. But perhaps the most mind-bending explanation lies in the fabric of space itself. Quantum mechanics tells us that even a perfect vacuum isn't truly empty. It seethes with virtual particles flickering in and out of existence. Could extreme gravitational effects or undiscovered quantum processes in these voids amplify this quantum foam into detectable gamma rays? It's a long shot, but if proven, it would revolutionize our understanding of how energy emerges from nothingness. The void gamma rays force us to confront an unsettling truth. We may be missing entire categories of cosmic phenomena. Whether the answer lies in dark matter's secrets, lone celestial outcasts, or new physics, one thing is certain: the universe's quietest corners are speaking. We just haven't learned their language yet. On August 17, 2017, the universe gave us a front-row seat to one of the most violent cosmic ballets ever witnessed, the collision of two neutron stars, an event so cataclysmic it sent ripples through space-time itself. Dubbed GRB 170817A, this explosion wasn't just detected in gamma rays. For the first time, gravitational wave observatories caught its signature shudder, marking a new era of multi-messenger astronomy. The data was a treasure trove, confirming theories about the origins of heavy elements like gold and platinum, forged in the furnace of this cosmic crash. Yet, years later, the afterglow of this merger continues to baffle scientists, revealing gaps in our understanding of how these extreme events unfold. The initial gamma-ray burst was surprisingly weak for a neutron-star merger, a short, sharp flash lasting less than 2 seconds. Normally, such collisions should produce longer, more energetic bursts, but GRB 170817 seemed almost subdued, as if the universe had turned down the volume on its own fireworks. Then came the afterglow, a lingering emission spanning X-rays, radio waves, and visible light. This fading echo behaved in ways no model had predicted. Instead of dimming steadily, it brightened unexpectedly weeks after the merger, like a smoldering fire suddenly flaring back to life. Even more puzzling was its trajectory. The jet of material unleashed by the collision appeared to be structured in a narrow, pencil-like beam, yet observations suggested it was also surrounded by a wider, slower-moving cocoon of debris. Theories abound to explain these oddities. One possibility is that we're seeing the aftermath of a failed jet, an ultra-relativistic stream of particles that struggle to punch through the dense wreckage of the merger. Picture a fire hose trying to plow through wet cement. The jet might have choked on its own surroundings, releasing energy unevenly. Another idea involves the birth of a magnetar, a neutron star with an unimaginably powerful magnetic field, spinning rapidly in the wreckage. Such an object could inject fresh energy into the system, reigniting the afterglow long after the initial explosion. But the deepest mystery lies in the energy budget. When scientists tallied up all the radiation, gravitational waves, and ejected material, the numbers didn't quite add up. A significant fraction of the energy seems to be missing, as if siphoned off into some invisible channel. Could it have gone into accelerating particles to near light speed, producing neutrinos we haven't detected? Or was it swallowed by the brief formation of a black hole, leaving no trace? GRB 170817 was supposed to be a textbook event, a chance to test decades of theories against reality. Instead, it's become a reminder that even our best models are rough sketches of the universe's chaos. Every anomaly in its afterglow is a clue pointing to physics we've yet to grasp, and as more mergers are detected, each one adds new wrinkles to the story, proving that when it comes to neutron-star collisions, the universe still has plenty of surprises up its sleeve. Deep in the gamma-ray sky, astronomers have caught traces of cosmic echoes, ghostly signals arriving thousands of years after the explosions that may have birthed them. These delayed gamma rays don't come from fresh supernova lighting up the night. They seem to be stragglers from stellar catastrophes that rocked our galaxy centuries or even millennia ago. It's as if the universe is playing a game of cosmic telephone, with whispers from the past only now reaching our detectors. The mystery hinges on a fundamental question: how do particles, protons, electrons, and atomic nuclei get accelerated to near light speed in the wake of a supernova? When a massive star dies, it doesn't just vanish in a flash. Its shock waves rip through surrounding gas and dust, creating turbulent magnetic fields that act like natural particle accelerators. These fields can slingshot charged particles to insane energies, turning them into cosmic rays. And when those particles collide with interstellar gas or starlight, they produce gamma rays, a process that should happen almost instantaneously after the explosion. But here's the twist: some gamma-ray sources appear to linger long after their parent supernova have faded to invisibility. Take the case of W44, a supernova remnant about 10,000 light-years away. Its gamma-ray emission isn't just coming from the shell of expanding debris, the expected hotspot, but from nearby molecular clouds seemingly untouched by the blast. The leading theory, cosmic rays accelerated by the supernova shockwave thousands of years ago, are still traveling through space, only now slamming into these distant gas clouds and sparking fresh gamma rays. Imagine a stone tossed into a pond, with ripples finally reaching the far shore long after the splash. This delayed emission throws a wrench into our models of particle acceleration. If cosmic rays can wander the galaxy for centuries before producing detectable gamma rays, it means they're either far more persistent or far more efficiently accelerated than we thought. Some simulations suggest that magnetic fields in supernova remnants might act like cosmic storage rings, trapping particles and keeping them energized for millennia. Others propose that these echoes come from secondary processes, where cosmic rays collide with other particles, creating unstable pions that decay into gamma rays far from their birthplace. The implications ripple beyond galactic astronomy. If ancient supernovae are still peppering the galaxy with high-energy particles, it could mean the cosmic ray environment near Earth isn't static but fluctuates over millennia, influenced by stellar explosions that happened before human civilization existed. Even more intriguing, these gamma-ray echoes might be the key to mapping invisible cosmic ray highways, filaments of high-energy particles winding through the Milky Way, unseen except when they collide with gas and light up in gamma rays. Every unexplained echo is a clue, a signpost pointing to gaps in our understanding of how energy propagates through the void. Whether from trapped particles, hidden accelerators, or something even more exotic, these delayed signals remind us that the universe's most violent events don't just vanish, they reverberate, leaving traces we're only beginning to decode. At the heart of our galaxy, where stars crowd so thickly they blur into a golden haze, lies a gamma-ray puzzle that defies every expectation. The galactic center excess, an unexplained surplus of high-energy light radiating from the Milky Way's core, shouldn't exist. At least not in the way we're seeing it. Unlike the structured Fermi bubbles or the diffuse gamma-ray background, this glow is concentrated, symmetrical, and too perfect, as if some unseen hand painted it into the cosmos. The most tantalizing explanation: dark matter annihilation. Picture the galactic center as a cosmic blender, churning with invisible particles. If dark matter gathers there in dense clumps, as simulations suggest, collisions between these particles could produce gamma rays in precisely the pattern we observe. It's like watching smoke rise from a hidden fire. We can't see the flames, but the evidence billows around us. The symmetry of the excess fits dark matter's expected distribution beautifully, as if the universe left us a breadcrumb trail to its most elusive substance. But not everyone's convinced. Skeptics point to a swarm of millisecond pulsars, dead stars spinning hundreds of times per second, lurking in the galactic center. These ultra-dense remnants emit gamma rays as they whip charged particles around their powerful magnetic fields. Individually, they're faint, but together, they could mimic the smooth glow we attribute to dark matter. It's the cosmic equivalent of mistaking a field of fireflies for a neon sign. The problem: we haven't found nearly enough pulsars to account for the excess, leaving astronomers to wonder, are we missing thousands of these dim objects, or is there something else at play? Then there's the cosmic ray wildcard. The galactic center is a maelstrom of high-energy particles, slamming into gas clouds and sparking gamma rays like a never-ending fireworks show. Some researchers argue that unusual gas distributions or turbulent magnetic fields could amplify these interactions, creating the illusion of an excess. Others propose more exotic culprits: primordial black holes, rogue antimatter annihilations, or even relics from the Milky Way's violent youth. What makes this mystery so gripping is the stakes. If the excess is dark matter, it's our best shot at finally nailing down its properties. But if it's pulsars or cosmic rays, it means the galactic center is even more extreme and poorly understood than we imagined. Every new observation tightens the knot, forcing us to confront just how little we know about the chaos lurking in our own backyard. One thing's certain: the answer, when it comes, will rewrite the story of our galaxy's hidden heart. Billions of years ago, some of the brightest objects in the universe, quasars, lit up the cosmos with the fury of supermassive black holes feasting on gas and stars. These galactic monsters should have faded into darkness long ago, their fuel exhausted. Yet modern telescopes catch whispers of their presence, faint gamma-ray emissions where no active quasar remains. These aren't just cosmic echoes, they're full-blown apparitions challenging our understanding of how black holes die, or if they ever truly do. Take the case of the quasar B2086+0156. Optical telescopes show nothing but a dim, ordinary galaxy where a brilliant beacon once blazed. But gamma-ray observatories tell a different story. An unmistakable glow persists, thousands of times brighter than the galaxy's stars could produce. It's as if the black hole's engine is still idling, running on fumes long after its last visible meal. The leading theory suggests these ghosts are powered by leftover material, dust, gas, or even dark matter slowly spiraling into the black hole's maw over eons. Imagine a campfire reduced to embers, still warm long after the last log burned away. But there's a problem with this tidy explanation. Some relic AGN emit gamma rays at energies that shouldn't be possible from such feeble accretion. One particularly baffling example is the object known as J1625+0265, a dead quasar whose gamma-ray output spikes unpredictably, as if something occasionally stokes its dying fires. These flares defy conventional models which predict dead quasars should fade smoothly, not flicker back to life. Could there be hidden mechanisms, perhaps magnetic fields trapping material in a decades-long delay? Or are we seeing the last gasps of stars torn apart by the black hole's residual gravity? Then there's the dark matter angle. Some theorists propose that these lingering gamma rays come not from black holes at all, but from annihilating dark matter particles concentrated in the galaxy's core. Quasars during their active phases might have funneled dark matter into dense clouds through gravitational interactions. Now, even with the quasar silent, those trapped particles continue to collide, producing gamma rays. It's an elegant idea, but it fails to explain why only some relic AGN show this emission while others remain dark. The implications ripple across cosmic time. If dead quasars can stay on at low power for billions of years, it means we've underestimated how long black holes can influence their galaxies. Their gamma-ray ghosts might be heating surrounding gas, suppressing star formation long after their brilliant heyday. Or perhaps we're seeing evidence of entirely new black hole states, phases of existence theoretical physicists haven't yet imagined. Every unexplained gamma-ray whisper from these cosmic tombs is a clue, hinting that even in death, the universe's most powerful engines still have stories to tell. Beyond our galaxy's bustling streets of stars and gas, the cosmic countryside should be quieter, less crowded, less chaotic. Yet when astronomers measure the gamma rays pouring in from deep intergalactic space, the numbers don't add up. This extragalactic gamma ray background, a faint but pervasive glow from every direction, shines brighter than the combined output of all known sources: blazars, star-forming galaxies, even the accumulated light from billions of supernova. It's as if we're hearing the hum of a hidden cosmic orchestra playing just beyond the edge of our perception. The first clue to this anomaly lies in the distribution. Unlike the Milky Way's gamma-ray hotspots, which cluster around pulsars and black holes, this background is eerily uniform, a smooth veil of high-energy light stretched across the entire sky. That uniformity rules out obvious suspects like rogue galaxy clusters or undiscovered blazars. Those would create telltale lumps in the signal, bright patches where they're concentrated. Instead, we're left with something far more enigmatic, a glow that suggests either countless faint sources blending together or a single, universe-wide process we've yet to identify. One leading theory points to star-forming galaxies in the early universe, back when cosmic gas was collapsing into stars at a breakneck pace. These young galaxies, brimming with supernova and pulsars, could have flooded space with gamma rays that took billions of years to reach us. The catch, even if we account for every star-forming galaxy in existence past and present, their combined output falls short. There's simply too much gamma radiation lingering between the galaxies, like smoke from a fire that burned hotter than any flame we've ever seen. Another possibility involves cosmic rays accelerated in the voids between galaxies. Picture vast, invisible rivers of high-energy particles funneled by intergalactic magnetic fields over millions of light years. When these particles collide with the sparse gas floating in intergalactic space, they could spark gamma rays, a faint but widespread emission that accumulates into the background we detect. The problem: current models suggest these collisions should produce other byproducts like X-rays, which we don't see in the expected amounts. Then there's the dark matter hypothesis. If dark matter particles annihilate or decay throughout the cosmos, they could be seeding the universe with gamma rays on a scale no single galaxy or cluster could match. This would explain the background smoothness. Dark matter is everywhere, after all, but it raises a thorny question. Why don't we see similar excess gamma rays from dark matter-rich regions like dwarf galaxies or the Milky Way's core? The truth might lie beyond known physics. Some theorists speculate about primordial black holes evaporating via Hawking radiation, or even exotic particle interactions from the universe's first seconds. Whatever the source, this anomalous background is more than a cosmic accounting error. It's a signpost pointing toward gaps in our understanding of how energy flows through the universe, gaps that might hide entirely new chapters in the story of the cosmos. Until we crack this puzzle, the space between galaxies will remain not just empty, but mysteriously, inexplicably bright. Scattered across the gamma-ray sky are mysterious bright spots, flashes of concentrated energy that defy explanation. These aren't the predictable bursts from pulsars or black holes. They don't align with known supernova remnants or galaxy clusters. Instead, they glow like cosmic streetlights in the void, marking intersections where something invisible is funneling unimaginable energies into space. Astronomers call them unassociated sources, gamma-ray hotspots with no obvious home, and they might be the universe's way of hinting at phenomena we've yet to imagine. Take the case of one particularly stubborn hotspot in the constellation of Orion. Fermi telescope data reveals a patch of gamma rays blazing 30% brighter than the surrounding background, yet optical and radio surveys show nothing but empty space. No neutron stars, no gas clouds ripe for particle collisions, just silence and that eerie, unexplained glow. One theory suggests we might be seeing the aftermath of a dark supernova, a hypothetical explosion where a massive star collapses directly into a black hole without the usual fireworks. In this scenario, most of the energy would be channeled into gravitational waves and high-energy particles, leaving little visible trace but a lingering gamma-ray signature. Then there's the puzzle of anisotropic clustering, a fancy term for hotspots that aren't randomly scattered but seem to gather along invisible lines or planes. If these were ordinary astrophysical sources, their distribution should be more chaotic, like sprinkles on a cupcake. Instead, some studies suggest they might trace the gravitational scaffolding of the universe, marking where dark matter filaments intersect and potentially interact. Picture a spiderweb glistening with dew. The gamma rays could be the dew, revealing strands of the cosmic web we've never directly observed. But the most tantalizing possibilities lie beyond known physics. Some hotspots emit gamma rays at energies that challenge the limits of our particle acceleration models. One extreme example, near the galactic plane, beams photons with energies exceeding 100 tera-electronvolts, equivalent to a baseball's kinetic energy squeezed into a single particle of light. Conventional astrophysics struggles to explain how anything short of a supermassive black hole's jet could produce such radiation, yet no black hole lurks nearby. Could this be evidence of cosmic strings, theoretical defects in spacetime left over from the Big Bang? Or perhaps the decay of primordial particles predicted by supersymmetry, finally making their presence known? The frustration and the thrill of these unassociated sources is their refusal to fit neatly into any box. Every time one mystery seems solved, like a faint, previously unnoticed pulsar finally linked to a hotspot, a dozen more remain, their gamma-ray glow taunting us with questions. Are they the smoke from hidden cosmic fires, the footprints of exotic particles, or simply a reminder that the universe, even in our era of precision astronomy, still holds cards it hasn't shown us? Until we peer deeper into these enigmatic bright spots, they'll remain both beacons and roadblocks, guiding us toward new physics while stubbornly guarding their secrets. Some cosmic objects don't just shine, they flicker like a faulty light bulb, pulsing with gamma rays in erratic bursts that mock our attempts to predict them. These aren't the steady ticks of pulsars or the predictable flares of feeding black holes. They're cosmic wild cards, blaring high-energy light one moment and vanishing the next, as if the universe itself can't decide how much energy to pour into them. Take the bizarre case of PSR J2021 plus 4021, a gamma-ray source in the constellation Cygnus. For years, it behaved like any other pulsar, spinning with clockwork regularity. Then, without warning, its gamma-ray emissions doubled in intensity for exactly 37 minutes before snapping back to normal as if nothing had happened. No change in rotation, no visible disturbance, just a sudden, unexplained surge of energy that defied every model of neutron star behavior. It's like watching a car idle smoothly, only for the engine to roar to life on its own, then instantly return to a purr. Then there's the enigma of ghost flares from supernova remnants. These ancient stellar corpses, long past their explosive prime, should emit gamma rays at a steady, decaying rate as their shockwaves slowly dissipate. Yet remnants like W51c occasionally spit out gamma-ray bursts brighter than their entire baseline emission, lasting mere hours before fading. The leading theory involves leftover cosmic rays particles trapped in magnetic turbulence for centuries, suddenly finding an escape route and colliding with gas clouds. But why these delays, and why do some remnants flare while others, nearly identical in age and structure, stay silent? The most mind-bending examples come from Blazar's supermassive black holes firing jets directly at Earth. While most fluctuate over months or years, a handful, like Biel-Lacerty, have been caught flickering on timescales of minutes. Here's the problem. Black hole jets are thought to originate from regions light days or even light weeks across. Changes that fast would require the entire jet to brighten in sync, like a stadium wave moving faster than the speed of light, a physical impossibility under current theories. Some physicists propose jets within jets, where smaller, ultra-fast substructures dance inside the main outflow. Others wonder if we're seeing light bent by space-time itself, warped by the black hole's gravity into deceptive flickers. The implications ripple far beyond these individual oddities. If cosmic accelerators can turn their output on and off like a switch, it means our models of particle acceleration, built on decades of steady, predictable sources, are missing critical physics. Maybe magnetic fields reconnect in ways we haven't imagined. Perhaps shockwaves propagate through interstellar gas in fractal patterns, creating chaotic pockets of extreme energy. Or could these flickers be hints of something deeper, like quantum processes playing out on macroscopic scales? Every erratic pulse is a crack in the foundation of astrophysics, a sign that the universe's most energetic engines still hold back their truest secrets. Until we crack the code behind their variability, these cosmic strobe lights will keep flashing their riddles across the void, bright, brief, and utterly perplexing. Imagine a galaxy where the lights are off, no stars, no glowing gas, just an empty void where visible matter should be. Yet when gamma-ray telescopes peer into these so-called dark galaxies, they catch faint but unmistakable flickers of high-energy light. It's like spotting a shadow that somehow shines, a cosmic contradiction that could rewrite our understanding of the universe's most elusive substance, dark matter. Dark galaxies are the universe's stealthy giants. They contain enough mass to rival the Milky Way, but almost all of it is invisible. No stars, no glowing nebulae, just vast clouds of hydrogen gas so faint they're nearly transparent. The only reason we know they exist at all is through their gravitational tug on neighboring galaxies. Yet a handful of these ghostly structures, like Segway 1 and Triangulum 2, defy expectations by emitting gamma rays. That's the puzzle. With no stars to power supernova or forge pulsars, where does this radiation come from? The leading suspect is dark matter annihilation. Picture trillions of invisible particles crammed into these galaxies' cores, colliding so frequently that a fraction of their mass converts into gamma rays. It's a tantalizing idea, finally, a way to see dark matter indirectly. The signal's smooth, spread-out nature fits this theory perfectly. Unlike point sources like pulsars, which produce sharp gamma-ray spikes, dark matter annihilation would glow diffusely, like a dim neon sign wrapped around the galaxy. But not all astronomers are convinced. Some argue these gamma rays could come from a sparse population of millisecond pulsars, the dense spinning remnants of dead stars. These objects are faint enough to evade optical detection but could collectively produce the observed signal. The catch: pulsars usually cluster in star-rich environments, not the near-empty voids of dark galaxies. And to match the gamma-ray data, these hypothetical pulsars would need to exist in numbers far exceeding predictions. Then there's the energy spectrum clue. Gamma rays from dark matter annihilation should peak at specific energies tied to the particle's mass. Some dark galaxies, like Draco, show hints of this fingerprint, but others, like Ursa Major 2, emit gamma rays that don't quite fit. Could there be multiple processes at work, or does dark matter behave differently in these isolated environments? The stakes couldn't be higher. If dark galaxies truly are gamma-ray factories, they might hold the key to identifying dark matter's particle nature. Are we seeing the aftermath of WIMP, weakly interacting massive particles crashing together, or something more exotic like actions or sterile neutrinos? Every unexplained photon from these starless voids forces us to question whether we're on the brink of a breakthrough, or if the universe once again is playing tricks on us. Until we solve this riddle, dark galaxies remain both a beacon of hope and a cosmic mirage, whispering secrets we can't yet decipher. Some of the universe's most energetic light shouldn't exist, at least not in the form we detect it. These are the tera-electronvolt gamma rays, photons packing 1 trillion times more energy than visible light, streaking across cosmic distances to reach our telescopes. But here's the catch: according to well-established physics, these gamma rays should have vanished long before they ever reached Earth. Their journey through the cosmos should be a suicide mission, ending in fiery annihilation against the sea of low-energy photons left over from the Big Bang, the cosmic microwave background. Yet they arrive anyway, bright and unmistakable, flouting our expectations like cosmic loopholes. Picture a high-energy gamma ray as a speeding bullet and the cosmic microwave background as a dense fog. According to Einstein's relativity, when these two photons collide, they can produce matter, specifically electron-positron pairs. This process, called pair production, should act like a cosmic sieve, filtering out the highest energy gamma rays over vast distances. And yet, observatories like the High-Energy Stereoscopic System in Namibia routinely detect these photons from sources billions of light-years away. It's as if bullets were passing through solid concrete walls without slowing down. So how do they survive? One possibility is that our understanding of pair production is incomplete. Maybe there's an as-yet undiscovered threshold where ultra-high-energy photons interact differently with the cosmic microwave background. Alternatively, the photons might not be traveling alone. Some theorists propose they're escorted by exotic particles, action-like entities that can oscillate into photons mid-journey, effectively tunneling through regions of space that would otherwise annihilate them. Imagine a spy changing disguises to slip past checkpoints. These gamma rays could be shape-shifting their way to Earth. Then there's the space-time warping explanation. If the fabric of the universe has subtle quantum fluctuations on tiny scales, these ripples might bend the paths of gamma rays just enough to reduce their chances of colliding with background photons. It's like weaving through a rainstorm and miraculously avoiding every drop. Even more radical is the idea that Lorentz invariance, a cornerstone of relativity stating that the laws of physics are the same for all observers, might break down at these extreme energies, allowing gamma rays to sidestep the usual rules. But perhaps the most tantalizing solution lies in the sources themselves. What if these gamma rays aren't primordial at all, but freshly minted closer to home? Some models suggest that cosmic rays protons accelerated to near light speed could collide with local gas or starlight, producing gamma rays just a short distance away. In this scenario, the detected photons aren't ancient survivors but newcomers, their apparent paradox merely an illusion of perspective. The TV paradox forces us to confront gaps in our knowledge that span from quantum mechanics to cosmology. Every detection challenges the boundaries of known physics, hinting at forces or phenomena we've yet to grasp. Whether the answer lies in new particles, spacetime's hidden wrinkles, or something even stranger, one thing is clear: the universe's most energetic light still has secrets to spill. And with each photon that shouldn't exist, the cosmos nudges us closer to rewriting the rules. Black holes aren't just cosmic vacuum cleaners sometimes, they're also master sculptors of light. Among the rarest and most mesmerizing structures in the gamma-ray sky are glowing rings, perfect circles of high-energy radiation encircling these gravitational monsters like halos. These aren't the chaotic jets or swirling accretion disks we're used to seeing. They're symmetrical, almost delicate, as if the universe paused mid-chaos to trace a geometry lesson onto the darkness. One of the most striking examples lies near the black hole at the heart of the galaxy Centaurus A. When the Fermi Gamma Ray Space Telescope imaged this region, it caught a faint but unmistakable ring stretching over 3,000 light-years across, far wider than the black hole's immediate influence. The odd part, there's no visible gas or dust at that distance to explain the structure. It's as though the black hole reached out and painted a target on the sky, leaving behind only gamma rays as evidence. So how does a black hole, an object famous for devouring light, create something so pristine? One theory points to shock waves. Picture material ejected during a past outburst, a jet of particles blasted outward at near light speed. When this jet slams into the thin gas lingering between galaxies, it could send a shock rippling through space, accelerating particles and triggering gamma-ray emissions in a perfect sphere. Think of it like a pebble dropped in a pond, except the pond is interstellar space and the ripples are made of pure energy. But there's another, even wilder possibility: magnetic mirrors. Some models suggest the black hole's powerful magnetic fields could act like lenses, bending stray gamma rays into circular paths. Imagine light trapped in a cosmic racetrack, looping around the black hole's poles until it escapes as a glowing ring. This would explain why some rings appear offset from the black hole itself, their centers hovering in empty space like a celestial bullseye with no arrow to mark the hit. The real puzzle is timing. These rings don't stick around, they fade over centuries, meaning we're catching them in a fleeting moment of cosmic performance art. That raises tantalizing questions. Are we seeing echoes of ancient black hole tantrums, or evidence of ongoing processes we've yet to understand? And why do only a handful of black holes sport these shimmering collars of light while most go without? Every gamma-ray ring is a frozen ripple in space-time, a snapshot of forces playing out on scales we can barely fathom. Whether sculpted by shock waves, magnetic gymnastics, or something even stranger, they remind us that even the darkest objects in the universe know how to shine, if only we know where to look. When a massive star explodes as a supernova, it's supposed to be one of the universe's most spectacular light shows. A burst of energy so intense it can outshine entire galaxies. So why do some of these cataclysmic events leave gamma-ray detectors eerily silent? It's as if the star staged its own disappearance, vanishing without leaving behind the high-energy fingerprints we've come to expect. This cosmic vanishing act isn't just a fluke, it's a clue that our understanding of stellar deaths might be missing a critical chapter. Take supernova 2005-18A, for example. When this star detonated in a nearby galaxy, telescopes caught every phase of its death throes. The flash of ultraviolet, the glow of radioactive nickel decaying into cobalt, even the shock waves rippling through surrounding gas. But gamma-ray telescopes, nothing. Not a single flicker of the high-energy radiation that should have accompanied the collapse of such a massive core. It's like watching a fireworks finale where the biggest rocket fizzles out mid-launch, leaving everyone staring at the sky in confusion. The silence speaks volumes. Gamma rays in supernova are supposed to come from radioactive elements forged in the explosion, like nickel-56 and titanium-44. As these unstable isotopes decay, they emit gamma-ray photons with distinct energy signatures, a sort of nuclear barcode that tells us what's happening inside the wreckage. When those signals are missing, it suggests something disrupted the process. Maybe the explosion wasn't powerful enough to synthesize those elements in the first place. Or perhaps the dying star's outer layers were so thick they absorbed the gamma rays before they could escape. But the plot thickens with supernova that do emit gamma rays, just not where or when we'd expect. Consider Cassiopeia A, the remnant of a star that exploded 300 years ago. Gamma-ray telescopes eventually detected titanium-44 in its debris, but the signal was oddly lopsided, concentrated in clumps rather than evenly distributed. This hints at a chaotic, asymmetric explosion where nuclear fusion sparked unevenly like a misfiring engine. If some supernova are more messy than others, it could explain why their gamma-ray output doesn't follow the rules. Then there's the wild card of stellar chemistry. Stars rich in heavier elements might die differently than their pristine, hydrogen-dominated counterparts. Their complex internal structures could stifle gamma-ray production or channel the energy into other forms, like neutrinos or gravitational waves. It's like comparing a dynamite blast to a controlled demolition, same raw power, but one leaves far less debris behind. The implications ripple beyond stellar physics. If we can't rely on gamma rays to track supernova, we might be underestimating how often these explosions occur. especially in distant galaxies where optical telescopes can't spot them. Worse, missing gamma-ray signals could skew our measurements of cosmic element production, throwing off calculations of how much iron, gold, and other metals the universe has forged over time. Every silent supernova is a reminder that the universe's most violent events don't always follow the script. Whether it's hidden absorption, turbulent explosions, or exotic stellar compositions, these gaps in our knowledge aren't just academic curiosities. They're windows into the chaotic, unpredictable nature of stellar death. And until we solve the mystery of the missing gamma rays, we're only seeing half the story written in the ashes of dead stars. Long before galaxies took shape and stars ignited, the universe was a seething cauldron of raw energy, and some of that primordial fury might still echo in the gamma rays we detect today. Hidden within the cosmic background could be signals from the first billion years of existence, photons that have traveled nearly the entire history of time to reach us. These aren't just random bursts, they're potential relics from an era when the cosmos was so young, it hadn't even finished lighting its first stars. Picture the universe in its infancy, a hot, dense soup of particles and radiation. As it expanded and cooled, protons and electrons combined to form neutral hydrogen, a period called the Cosmic Dark Ages. Then, around 200 million years after the Big Bang, the first stars flickered to life. These weren't like the stars we know today. They were behemoths, hundreds of times more massive than our Sun, burning furiously and dying young in spectacular supernova that flooded space with gamma rays. If we could isolate those ancient signals, they'd offer a direct window into the universe's fiery adolescence. The challenge, untangling these whispers from the noise. The gamma-ray background is a palimpsest, layer upon layer of emissions from billions of years of cosmic activity. But subtle anomalies in the background spectrum, tiny excesses at specific energies, might betray their presence. Some theorists suggest these could be fingerprints of population 3 stars, the hypothetical first generation of stars made purely from hydrogen and helium. These stars would have burned at temperatures so extreme, their deaths could have produced gamma rays with unique signatures like cosmic fossils embedded in the sky. Then there's the dark matter angle. In the early universe, dark matter was denser and particle collisions would have been far more frequent. If those annihilations produced gamma rays, their light might still linger, stretched and faded but detectable as a faint overlay on the modern gamma ray background. It's like hearing a distant chorus from the dawn of time, its notes redshifted but still discernible beneath the cacophony of younger sources. Even more tantalizing are hints of gamma rays from the universe's very first black holes. Primordial black holes forged in the chaos of the Big Bang itself might have evaporated via Hawking radiation, releasing gamma ray bursts as they died. Alternatively, supermassive black holes in the cores of early galaxies could have launched jets powerful enough to pierce the surrounding gas, flooding the cosmos with gamma rays that now contribute to the background. The trouble is, we don't know exactly what those first black holes looked like or how they behaved, which means every anomaly in the background could be a clue waiting to be decoded. The real breakthrough will come when next-generation telescopes, like the proposed Amigo mission, combine sharp angular resolution with unprecedented sensitivity. These instruments might finally tease apart the background's components, separating the primordial wheat from the astrophysical chaff. Until then, the gamma-ray background remains a cosmic cipher, its oldest layers whispering secrets we're only beginning to grasp. And if we're right, if those whispers truly hold echoes from the universe's first breath, then decoding them could rewrite the story of how everything began. One of the strangest patterns in the gamma-ray sky is what isn't there: the conspicuous absence of high-energy light in the universe's emptiest regions. While most of space crackles with faint gamma radiation, the vast cosmic void's gigantic bubbles of near-nothingness stretching hundreds of millions of light-years stand out as eerie quiet zones. It's as if the universe drew a map and deliberately left these areas blank, raising a tantalizing question. Why would gamma rays, of all things, respect borders we can't even see? This anti-correlation is more than a curiosity, it's a potential window into how the cosmos organizes itself on the grandest scales. Cosmic voids aren't just random empty patches. They're the inverted skeletons of the universe, tracing where matter isn't while revealing the hidden architecture of dark matter filaments and galaxy clusters. When gamma rays avoid these voids, it suggests their journeys are shaped by something beyond individual sources. Imagine tossing confetti into a gusty wind. The way it scatters isn't random but tied to invisible currents. Similarly, gamma rays might be tracing the universe's hidden scaffolding, their absence in voids hinting at forces we've yet to quantify. One explanation ties back to cosmic rays, those high-energy protons and atomic nuclei racing through space. In dense regions like galaxy clusters, cosmic rays constantly collide with gas and starlight, producing gamma rays as a byproduct. But voids, by definition, lack this raw material, no gas clouds to smash into, no stellar radiation to interact with. It's like expecting sparks from a flint struck in thin air. Yet this alone doesn't fully explain the sharpness of the anti-correlation. Even accounting for voids' emptiness, some gamma rays should leak in from surrounding structures unless something's actively filtering them out. That something might be magnetic fields. Recent simulations suggest the voids could harbor faint but expansive magnetic fields, woven into their fabric during the universe's infancy. These fields might deflect incoming cosmic rays, steering them away before they can produce gamma rays locally. Picture a cosmic maze where charged particles are rerouted by invisible walls, leaving the voids dark. If true, this would imply that voids aren't truly empty. They're threaded with subtle forces that shape the flow of energy across the cosmos. But the plot thickens when you consider alternative origins for gamma rays, like dark matter annihilation. If gamma rays were primarily coming from dark matter, their distribution should mirror the underlying density of invisible matter, which does extend into voids, albeit thinly. The fact that gamma rays still avoid these regions suggests dark matter alone can't explain the pattern. Unless, of course, dark matter behaves differently in voids, perhaps due to lower collision rates or unknown environmental factors. The implications ripple far beyond gamma rays. If voids actively suppress high-energy emissions, it means these regions aren't passive gaps but dynamic players in cosmic evolution. They might influence how energy propagates across the universe, how cosmic rays travel, even how large-scale structure forms. Every gamma ray desert is a clue, a silent witness to the unseen rules governing the cosmos. And until we decode why these voids stay dark, we're missing a critical piece of the puzzle, one that might redefine our understanding of the universe's invisible framework. Deep in the cosmic static, some gamma-ray signals don't play by the rules, tiny anomalies in energy and distribution that refuse to fit known astrophysical processes. These peculiar whispers have sparked a radical idea. What if they're not from stars or black holes at all, but from particles so exotic they've never been detected? Enter the world of actions, sterile neutrinos, and other hypothetical matter, ghostly entities predicted by quantum physics that might finally be making their presence known through these faint, high-energy fingerprints. Take actions first, theoretic particles originally conjured up to solve a puzzle in quantum mechanics. Unlike protons or electrons, actions would barely interact with normal matter, drifting through walls and planets like they weren't even there. But in the presence of ultra-strong magnetic fields, like those around neutron stars or galaxy clusters, actions could transform into gamma rays mid-flight. Picture a chameleon crossing a beam of light, flickering into visibility just long enough to leave a trace before vanishing again. That's exactly what some astronomers think they're seeing in certain gamma-ray signals, unexplained spikes around magnetars and quasars that align eerily well with action conversion models. Then there's the enigma of sterile neutrinos, a hypothetical heavier cousin to the neutrinos we know. These particles could be lurking in the hearts of galaxies, decaying into pairs of gamma-ray photons over astronomical timescales. If they exist, they'd solve two mysteries at once: the nature of dark matter and the origin of odd gamma-ray excesses in places like the Milky Way's core. The telltale sign, a faint monochromatic glow at specific energies, like a tuning fork humming a single note across the cosmos. Detectors have glimpsed hints of this signature in stacked galaxy clusters, but the signal remains frustratingly just out of reach, buried in noise. The boldest theories go even further. Some physicists speculate that gamma rays could be the decay products of primordial particles, relics from the universe's first seconds that have hung around undetected for 13 billion years. These particles, with names like Kaluza-Klein photons or WIMP, might cluster in regions of high dark matter density, occasionally annihilating into gamma-ray flashes. When telescopes catch unexplained bursts from dark galaxies or voids, it's possible we're witnessing the last faint sighs of these ancient entities. Of course, skepticism runs deep. Critics argue that action and sterile neutrino signals could easily be mundane astrophysics in disguise, unmodeled pulsar emissions, turbulent gas clouds, or instrumental artifacts. After all, the history of science is littered with new physics claims that crumbled under scrutiny. The real test will come when next-generation telescopes like the Advanced Gamma-Ray Imaging System begin operating, offering the precision needed to separate exotic particle signatures from cosmic background noise. What makes these theories so compelling isn't just their audacity, it's the stakes. If gamma rays are whispering the secrets of exotic matter, we're not just solving a cosmic puzzle. We're rewriting the inventory of the universe, proving there's an entire shadow world of particles weaving through reality, invisible until they flare into gamma-ray light. Every anomalous photon is a potential Rosetta Stone, waiting to translate the language of the unseen into terms we can finally understand. Gamma-ray bursts and supernova should be cosmic partners, two sides of the same catastrophic coin. When a massive star collapses, it's supposed to either explode as a supernova or generate a focused gamma-ray jet, depending on how its core behaves. Yet the universe loves exceptions, and the relationship between these phenomena is far messier than textbooks suggest. Some gamma-ray bursts arrive hand in hand with supernova, their light curves overlapping like synchronized fireworks. Others strike alone, leaving no trace of a stellar explosion behind. This cosmic mismatch isn't just a quirk, it's a fundamental challenge to how we understand the depths of the universe's most massive stars. Take the iconic case of GRB 980425 and its companion supernova SN 1998BW. Here, the gamma-ray burst and supernova were so tightly linked that their light curves blended seamlessly, proving for the first time that at least some bursts arise from collapsing stars. The mechanism seemed clear. As the star's core imploded into a black hole or neutron star, jets of material punched through the outer layers at near light speed, producing gamma rays while the rest of the star erupted as a supernova. It was a textbook example until the universe threw in a plot twist. Just 3 years later, GRB 060614 erupted in a galaxy 760 million light-years away. Telescopes scrambled to catch the expected supernova and found nothing. No ultraviolet bump in the afterglow, no radioactive nickel decay signature. Just silence where there should have been a stellar cataclysm. This wasn't a fluke. Dozens of similar, orphan bursts now pepper the records, their gamma-ray fury untethered from any visible explosion. At first, astronomers assumed these might come from mergers of neutron stars, which don't produce supernova. But many occur in star-forming regions, exactly where massive stars live and die. The leading explanation involves stellar zombie stars that collapse so completely they leave almost no trace. In these scenarios, a massive star's core might implode directly into a black hole without triggering the shockwave that normally rips the outer layers apart. The jets still form, drilling through the star's carcass to create a gamma-ray burst, but the supernova fizzles before it can begin. Picture a firework dud. The fuse ignites, but instead of bursting into color, it only sputters a weak spark before vanishing. But even this neat solution has cracks. Some supernova produce gamma-ray bursts days or weeks after the initial explosion, as if the central engine takes time to spin up. Others, like SN 2011KL, unleash unusually weak gamma-ray flashes mid-explosion, blurring the line between bursts and supernova entirely. The most extreme outliers are superluminous supernova, which shine 100 times brighter than normal but rarely produce gamma rays at all. It's as if the universe has multiple playbooks for stellar death, each with its own rules. The implications ripple through astrophysics. If gamma-ray bursts don't always signal supernova, or vice versa, it means our classification system for stellar explosions is oversimplified. We might be missing entire categories of core collapse events that don't fit the mold. Even more troubling, this disconnect could skew our measurements of star formation rates in the early universe, where gamma-ray bursts serve as cosmic beacons. Are we misreading the universe's history because we've assumed these phenomena are linked more tightly than they truly are? Every mismatched burst and supernova is a clue, hinting at hidden diversity in how stars die. Whether it's variations in stellar rotation, magnetic fields, or metallicity, something subtle yet profound is steering these explosions down different paths. Until we crack this code, the relationship between gamma-ray bursts and supernova will remain one of astrophysics' most tantalizing loose ends, a cosmic dance where the partners sometimes move in sync and other times refuse to acknowledge each other at all. Some galaxies shine with lighthouses of a kind we've never seen in our own beacons of gamma rays so steady and persistent, they defy every category astronomers have devised. These aren't the fleeting bursts of colliding neutron stars or the erratic flares of feeding black holes. They pulse with metronomic regularity year after year, as if some cosmic engineer fine-tuned them to outlast the stars themselves. And the strangest part, nothing in the Milky Way, no pulsar, no quasar, no known object behaves quite like them. One of the most enigmatic examples lies in the galaxy Messier 82, a chaotic starburst region 12 million light-years away. Here, a gamma-ray source dubbed M82X2 has been shining uninterrupted for decades, fluctuating in brightness but never vanishing. At first glance, it resembles a microquasar, a small-scale version of the jets seen around supermassive black holes. But the details don't add up. Its spectrum is all wrong, peaking at energies far higher than typical microquasars, and its emission region is suspiciously compact, as if the energy emerges from a single pinpoint in space. It's like finding a candle that burns with the intensity of a wildfire, yet never melts its own wax. Then there's the mystery of NGC 1265, a distant galaxy hosting a gamma-ray emitter that flickers in a rhythmic 400-day cycle. This isn't the rapid spin of a pulsar or the chaotic variability of a blazar. It's something in between, a slow, steady heartbeat of high-energy light with no visible counterpart. Some theorists suggest it could be a supermassive black hole with an unusually stable accretion disk, its jets wobbling like a spinning top as they sweep across our line of sight. Others propose a binary system where a black hole or neutron star orbits a companion star, its gravity funneling material into a gamma-ray emitting shockwave at precise intervals. But no model fully explains why the signal is so clean, so immune to the turbulence that plagues other cosmic accelerators. The real outliers, though, are the naked gamma-ray sources, objects like the one in galaxy IC 310, which blazes with gamma rays but shows no sign of X-rays, radio waves, or visible light. In our cosmic neighborhood, gamma-ray emission almost always comes packaged with other forms of radiation. A pulsar might emit gamma rays from its poles while glowing in X-rays across its surface. A black hole's jet typically radiates across the spectrum, but these distant beacons break the rules, shining in gamma rays alone as if they've stripped away every other wavelength. It's like hearing a singer's high notes without the rest of the melody, disembodied and unsettling. What makes these objects so baffling isn't just their strangeness, but their stubborn refusal to fit existing frameworks. They're not rare enough to dismiss as flukes, yet not common enough to form a clear pattern. Some might be extreme versions of known objects, pushed beyond recognized limits by environments more violent than the Milky Way's. Starburst galaxies like M82, for instance, breed stars at breakneck speeds, creating conditions ripe for freakishly powerful cosmic accelerators. Others could represent entirely new classes of objects, black holes spinning at unheard-of rates, or neutron stars wrapped in exotic magnetic fields that channel energy into gamma rays with unnatural efficiency. The most tantalizing possibility, we're seeing the handiwork of physics beyond the standard model. Certain theories predict the existence of quark nova, stellar explosions where neutron stars collapse further into ultra-dense quark stars, releasing bursts of gamma rays in the process. Others speculate about electromagnetic black holes, hypothetical objects where gravity and electromagnetism intertwine in ways that distort our usual understanding of radiation. These ideas are speculative, but when the universe keeps showing us gamma-ray sources that shouldn't exist, it's worth asking if we're missing a fundamental piece of the puzzle. For now, these extragalactic lighthouses remain cosmic riddles, their steady glow both a beacon and a challenge. Every flicker, every spectral anomaly is a clue waiting to be deciphered, a signpost pointing toward phenomena we've yet to name or understand. And until we do, they'll keep shining across the void, reminders that even in a universe we've mapped in exquisite detail, there are still corners where the rules we know don't seem to apply. For decades, astrophysicists have been hunting for a spectral line in gamma rays so distinct, it would act as a cosmic fingerprint, unmistakable proof of dark matter's existence. These lines wouldn't come from stars or black holes, but from the annihilation or decay of invisible particles, glowing at precise energies like neon signs in the void. The logic is simple. If dark matter is made of WIMP or actions, their collisions should produce gamma rays at sharply defined wavelengths, creating spikes in the data so clear they'd cut through the noise like a scalpel. But despite scanning the sky with increasingly sensitive instruments, from the Compton Gamma Ray Observatory to Fermi's LT, the universe has refused to hand over this smoking gun. The challenge lies in nature's reluctance to cooperate. Imagine tuning a radio across static, searching for a single pure tone buried in the hiss. That's what astronomers face when sifting through gamma-ray data, where potential signals are dwarfed by backgrounds from pulsars, cosmic rays, and distant blazars. Even more frustrating, some early hints like the infamous 130 giga-electronvolt line glimpsed near the galactic center faded under scrutiny, likely statistical flukes or artifacts of instrumental noise. It's as if the cosmos is teasing us, dangling spectral mirages before they dissolve into the chaos of the gamma-ray sky. Yet the hunt presses on because the stakes are so high. A confirmed line wouldn't just reveal dark matter's existence, it would unveil its mass and quantum properties. For instance, a spike at 511 kilo-electronvolts could indicate electron-positron pairs from light-dark matter annihilations, while a line at 3.5 giga-electronvolts might point to heavier WIMP. Each energy corresponds to a different particle, meaning every unexplored wavelength is a door to an entirely new physics. The absence of lines, though, speaks volumes too. It's forced theorists to reconsider assumptions. Perhaps dark matter particles don't annihilate directly into gamma rays, but into intermediate particles that cascade down. Or maybe they decay so slowly their gamma ray whispers are too faint for current detectors, Some models even suggest dark matter might be sterile, interacting so weakly that its spectral signature is inherently undetectable. These dead ends aren't failures, they're guideposts narrowing the labyrinth of possibilities toward answers that might lie beyond our current technological grasp. New missions like the proposed E-astrogam or the Advanced Compton Telescope aim to probe deeper, with resolutions sharp enough to separate potential lines from the background's fog. Until then, the search for gamma-ray spectral lines remains one of astrophysics' most high-stakes games of hide and seek, a pursuit where every null result brings us closer to understanding what dark matter isn't, even as its true nature continues to elude us. The hunt for answers about the cosmic gamma-ray background and the 25 mysteries surrounding it is far from over. In fact, we're on the brink of a revolution in how we see the high-energy universe, thanks to a new generation of telescopes designed to peer deeper, sharper, and more precisely than ever before. Leading the charge is the Cherenkov Telescope Array, or CTA, a global network of over 100 telescopes spread across the Canary Islands and Chile. Unlike traditional gamma-ray observatories which detect photons directly, CTA captures the fleeting blue flashes created when gamma rays slam into Earth's atmosphere. This allows it to pinpoint sources with unprecedented resolution, like swapping a blurry security camera for a high-definition telescope. With CTA's eye, we could finally resolve whether Fermi bubbles are fueled by dark matter or ancient black hole outbursts, or even catch gamma-ray echoes from the universe's first stars. Then there's AMIGO, the all-sky medium-energy gamma-ray observatory, set to launch in the next decade. Where Fermi saw the sky in broad strokes, AMIGO will paint in fine details, bridging the gap between low-energy and high-energy gamma-rays. This is crucial because many cosmic puzzles like the strange spectra of rogue neutron stars or the whispers of relic dark matter hide in the middle ground of gamma-ray energies. AMIGO's sensitivity could reveal whether actions are converting into gamma rays around magnetars or if primordial black holes are evaporating in distant voids. It might even catch the first gamma-ray signatures of quantum gravity tiny spacetime fluctuations that could distort high-energy photons as they travel across the cosmos. But perhaps the most exciting prospect isn't just solving existing mysteries. It's discovering ones we haven't even thought to ask. History shows that every leap in observational power unveils new enigmas. When Fermi launched in 2008, no one predicted the Fermi Bubbles or the galactic center excess. Similarly, CTA and AMIGO could expose cosmic phenomena that defy current theories. Gamma-ray rings around unknown objects, flickering signals from extra dimensions, or even patterns suggesting gamma rays are encoded with information from other universes. The future of gamma-ray astronomy isn't just about better tools, it's about rewriting the cosmic rulebook. With each new telescope, we're not just closing gaps in our knowledge, we're tearing open new ones, proving that the universe's most energetic light still has stories left to tell. And as these instruments come online, one thing is certain: the greatest mysteries of the gamma-ray sky may still be waiting in the dark just beyond the edge of our vision. From the ghostly glow of the cosmic gamma-ray background to the enigmatic pulses of orphaned neutron stars, we've journeyed through 25 of the universe's most baffling high-energy mysteries. Each one isn't just a curiosity, it's a crack in the foundation of our cosmic understanding, a signpost pointing toward physics we've yet to grasp. The Fermi Bubbles remind us that our own galaxy harbors secrets we're only beginning to unravel, while the gamma-ray whispers from dark galaxies tease us with the possibility of finally glimpsing dark matter's elusive nature. The orphaned bursts that arrive without supernova, the voids that refuse to glow, the ancient echoes of the first stars, all these mysteries are more than puzzles. They're invitations to look deeper, to question harder, and to admit that for all we've learned, the universe still holds cards it hasn't shown us. Perhaps the most humbling lesson is how interconnected these enigmas are. The missing link between cosmic rays and gamma rays isn't just a technical detail, it's a clue to how energy flows through the cosmos. The spectral lines we can't find might be hiding not just dark matter's identity, but entirely new laws of physics. Even the quietest supernova and the loneliest gamma-ray hotspots force us to reconsider what we thought we knew about stellar life cycles and the architecture of space itself. Every gap in our knowledge isn't an empty space, it's a doorway. So where do we go from here? The answer lies in curiosity. Maybe you're captivated by the idea of primordial black holes flickering into gamma rays as they evaporate, or you can't stop thinking about the magnetars that defy physics with their violent flares. Whatever mystery pulls you in, that's where the next breakthrough might begin. Share your favorite in the comments. Let's geek out over the universe's unsolved riddles together. And if you crave more deep space enigmas, hit subscribe so you're the first to know when we uncover new cosmic clues. Because here's the truth, the universe isn't just stranger than we imagine. It's stranger than we can imagine, and that's what makes the hunt so thrilling. The day we stop finding gamma-ray mysteries isn't the day we've figured everything out, it's the day we've stopped looking closely enough. So keep questioning, keep wondering, and above all, keep staring into the cosmic dark. Who knows what invisible light might finally flicker into view?